Hi, welcome to video 3.9a, Introduction to Differentials. Okay, so differentials is a way to approximate the change in the y value as you move from the point xy on the graph of f to a point x plus delta x, comma f of x plus delta x, where delta x is very small. So if you look at a picture right here, I have a curve, y equals f of x. I have a point on this curve, x, comma f of x. I have another point on this curve, which is f of x plus delta x, x plus delta x, comma f of x plus delta x. So if this is x, from here to here is x, and I add delta x. Now it's supposed to be very tiny, but if I drew it too small, you wouldn't be able to see anything. So if this is x, and I add delta x to it, then this new coordinate is x plus delta x. So that's the x coordinate of this point on that blue graph. And of course, the y-coordinate is what we would call f of x plus delta x. Now, if you look at the height of this point, which is at a height of y, if you wish, or f of x, and the height of this point, which is basically f of x plus delta x, which means it's the height y, which is the height we were at here, plus this extra height here, delta y. So delta y is the actual change in y on the graph of x, f of x, as you move from the point where x equals x to the point where x equals x plus delta x. So that's delta y. If now I was to draw this green tangent line, it's a tangent line tangent to my curve f of x at the point of tangency x f of x. What happens here is if you look at the green line and you looked at rise over run, well, of course, that would be the slope of the green line. But we know that the slope of a tangent line is also called dy dx. So therefore, the rise is dy, which is this little green height here, and this is dx. Now, as it turns out, dx and delta x are the exact same thing. But dy is an approximation of delta y. And you can see that the smaller and smaller delta x is, the closer and closer these 2 points are to the blue point. And you can see the height of the black point would be very close to the height of the green point. So what happens is your height dy and your height delta y, as you move closer and closer and closer to the points of tangency, the heights are very, very close together. So the dy by itself, just dy, is called the differential of y. Delta y, of course, is the actual change in y. Okay, if you look at it algebraically, if you look at the green on the left, you know that dy dx is the same thing as f prime of x. If I accept the existence of dy and dx as separate entities, you can see that if I multiplied both sides by dx, my dx's would cancel, leaving me with the differential of y on the left, and the right side I'd have f prime of x dx. So, for example, if you're given f of x equals x cubed, and the question is find dy, what you can look at it two ways. You can learn this formula, dy equals f prime of x dx, and go, oh, if f of x is x cubed, f prime of x is 3x squared times dx. I think it's easier to just go from f of x equals x cubed to f prime of x equals 3x squared. In other words, dy dx equals 3x squared. In other words, just multiply both sides by dx to isolate the dy. Okay. Now, here's an example of how this is used. So let's take that function, f of x equals x cubed. Its derivative, by the way, is 3x squared. Let's look at the point 2, 8 on the graph of f of x. If it might say the following, it might say approximate the actual change, but approximate it. So emphasis on the word, don't find the actual change, but approximate the actual change in y as y moves from 2.8 on the graph of f of x to a point 2.001 comma whatever it is. Okay, so we know that our delta x, which is the same thing as our dx, is the ugly number, which is the one with the decimals, minus the pretty number 2. And that is a small change in x, which is a positive change. Keep in mind, if I'm going from 2 to 2.001, I'm moving to the right by 0.001. So that's why you're always going to take the ugly minus the pretty. Okay, we know our formula that we learned says that delta y is approximately equal to dy. Okay, so the actual change is delta y. The approximate change is dy. So what is dy? Remember, dy is f prime of x dx. So here was our f of x. Our f prime of x is 3x squared. So we're going to have f prime of x, which is 3x squared at the pretty number, which is the 2, times the delta x or dx, which is the 0.001. And what you'll find out is that's 4 times 3 is 12 times 0.001 is 0.012. So what that's telling you is that as you move from the 0.28 to the 0.001 comma, whatever it is, the height is changing approximately by 0.012. So the approximate height of this point is the original height of 8 plus this delta y, which we have approximated to 0.012. Okay, so again, just the same old thing. Delta y is approximately equal to dy. dy is the approximate change in y. Delta y is the actual change in y. Here's where it might say you have a cube. Find the approximate change in volume as the edge of the cube increases from 3 to 3.1 inches using differentials. So draw a picture. We have a cube. All the sides measure the same thing. The volume of the cube is x cubed because it does say find the approximate change in the volume. By the way, when it says find the approximate change in the volume, that means find dv. It means find the differential of v. So all I do is I take the derivative of each side with respect to x. I get dv dx equals 3x squared. And then I get rid of the dx by sending it to the other side. And they've asked me to approximate the change in the volume. Well, I know that the actual change in the volume is approximated by the differential of the volume. So I now plug in the x, which was the 3, which is where you started at. It's the pretty number. The delta x, of course, if I went from x to 3 to 3.1, that means my delta x is 0.1. And then you simplify this and you find out that the approximate change in the volume as the edge grows from 3 inches to 3.1 inches will be approximately 2.7 cubic inches. Now, they could also ask you for the actual change in volume. Well, that means find the volume when the edge is 3.1 and subtract from it the volume when the edge was 3. So that would be actual calculations, and you can see that the actual change in volume is 2.791, and we were pretty close with our approximate change. Okay, so this is just a picture of what it looked like. Here was the original cube with its volume of 27. Here's the new cube with its volume of 29.79. That's the actual increase in the volume. Okay, so once again, same old, same old. Delta y is approximated by dy. dy is f prime of x dx. The x here is the original pretty x. This is the difference between the two x values. The dx will be positive if x is increasing, negative if x is decreasing. Remember, delta y is the actual change in y, dy is the approximate change in y. So in 7 through 10, it says use the given information to evaluate and compare delta y and dy. So number 8, they give you the function y equals 1 minus 2x squared. They give you a starting point, x equals 0. Is the x coordinate the starting point, and they're giving you your delta x, which is your dx, which is negative 0.1. Okay, so the 2 points we have are 0, comma, whatever f of 0 is, which I have f of x, so I find out from the point 0, 1. And then what they want me to do is go 0.1 to the left of that. So that would now be the point negative 0.1, comma, f of negative 0.1. So if I actually plug in negative 0.1 into here, I'll get 0.98. So what is delta y? Delta y is the actual change in the y, which is what's the new y value, the f of x plus delta x minus the old y value, which is f of x. X being the pretty number 0, and your delta x is negative 0.1. So this becomes f of 0 plus negative 0.1, which is f of negative 0.1, minus f of x, which is f of 0. F of negative 0.1 turns out is 0.98. which we already found here, minus an f of 0 is 1. So the actual change in y is negative 0.02. But they also want dy, so dy is an approximation of delta y, so it should be somewhere near negative 0.02. That's equal to f prime of x dx, which is f prime of our pretty number 0 times our delta x, which ends up being, remember our f of x was 1 minus 2x squared, so our f prime of x is negative 4x. Plug in the 0, and here's your dx, and you get an answer 0, which is close to negative 0.02, indeed. Okay, this is just find the differential. You're just going to rewrite this with positive rational exponents. You're going to take d dx of each side, just like you used to. It's just one extra step, just isolate the dy. Okay, so very straightforward, and that's the end of video 3.9a.